Hello and welcome to this presentation on an introduction to linear graphs. We're going to consider lines of the form of y equals mx plus c, the equation of a linear line, and we will plot graphs of y on the vertical axis against x on the horizontal axis. This presentation is essentially in two parts. Initially we'll be given the equation of the line in the form y equals mx plus c, and we'll generate various points from this equation and we'll plot them on our xy graph. The second part of the presentation relates to be given some data which we will plot on a graph, and we will put the best fit line we can through these points, and from that we will find the equation of the line y equals mx plus c. So the first part of the presentation is plotting a linear line from a given equation, and the second part of the presentation is plotting a linear line from given data. The two-dimensional graphs we're going to consider within this presentation are sometimes termed Cartesian graphs. They have two axes, x usually on the horizontal axis and y on the vertical axis. Graphs are pictorial representations of various information. Graphs are very useful because they show relationships between sets of data. In our two-dimensional Cartesian graph, we often say that y values are being plotted against the x values, as shown in the illustration below. The y variable is being plotted against the x variable. In this particular case, this is the line plotted of y against x. Here's some basic terminology associated with graphs. The vertical axis is usually termed the y-axis, and the y-axis contains what's termed the dependent variable. So the positive y values are shown in this direction, and negative y values are shown in this direction. The horizontal axis is where we plot the x values. The horizontal axis is usually termed the independent variable. Notice that x in the positive sense goes from left to right here, and x in the negative sense goes from right to left. The origin is located here where the x and the y-axis intersect. That's usually defined as point 0, 0. Notice when we define the coordinate of a point, we term them as x, y. So for the coordinate of point P, shown here, 3, 4, we read that as x, y. So in this case, the 3 is on the horizontal axis, the x-axis, 4 is the y value, and that's on the vertical axis. A coordinate can also be defined as x, y, and z, of course, in 3 dimensions, but we're just going to look at two-dimensional graphs within this presentation. So what we have here is an illustration of the y values on the vertical axis being plotted against the x values on the horizontal axis. Let's consider linear functions, because graphs can also represent functions. The simplest function is known as a linear function, and that's got the form of y on the vertical axis is equal to m multiplied by x plus c, where m in this equation is known as the gradient or the slope of the line. The plus c constant is termed the intercept value of the line with the y-axis. To find the gradient of a line, we simply take any 2 points that lie on the line. We work out the vertical distance between the 2 points, often called delta y. We work out the horizontal distance between the 2 points, often termed delta x. And we divide the delta y by the delta x. So that calculates the gradient or the slope of the line m. If I now label this point on the line as point 1, and this point on the line as point 2, the y value for point 1 on the vertical axis, that's 50. Considering the y value on the vertical axis for point 2, we can see that's clearly 20. So 50 minus 20 is a value of 30. So delta y for this line is 30. If we now consider point 1 and look at the x value on the horizontal axis, that's 5 and for point 2 the x-axis value is reads 0. So the value of delta x in this case is 5. Now we could work out the gradient m. The gradient m is equal to 6, and we can clearly see the intercept, which is the intercept of the line with the y-axis, is 20. So in this particular case, the equation of the line is y is equal to 6x plus 20. That's in the form of y equals mx plus c. We'll consider in greater detail the process for finding the equation of the line later on in this presentation. But that gives an insight in how to find the equation to a straight line. We're going to start with an exercise here whereby we are given an equation of the form y equals mx plus c, and we're asked to plot this equation on a graph. In fact, within this exercise 1, there are actually 4 graphs to plot, labelled A, B, C and D. So what the exercise wants us to do is to work out various coordinates for each of the equations. We're going to plot these equations on a graph. I want to work through the first equation with you, the y equals to the 2.5x plus 1.5. And then I will leave you to work out the coordinates associated with the line stated in B, C and D. Note in the question we're asked to plot between x is plus or minus 2 using increments of unity. So what that means is that we're going to plot our graph between x is equal to negative 2 and x equal to positive 2 using steps or increments of 1. So to help structure this solution, I've constructed a table below. So A, the function given is y is equal to 2.5x plus 1.5. We're plotting between x values of negative 2 and positive 2 in increments of 1. So we're going to have 5 points to plot on our graph later on. Well, we know that the equation for a linear line is y is equal to mx plus c. And our equation is the form y equals 2.5x plus 1.5. So in this particular case, just by inspection of the equation given, the m is going to be 2.5. And the c in our case, the constant, is positive 1.5. Always remember the sign in front of the numbers with it, so this is a positive 1.5. So now we're going to calculate the coordinates. When x equals to negative 2, the y value has already been calculated for us. It's negative 3.5. I will show you how to work some of the other coordinates out, and you can check this first coordinate here for yourself later on. Let's take the point 0, because that's an easy one for us to do first of all. So when x equals to 0, all we do now is put the value of x into the equation given. So y is equal to 2.5 multiplied by x, and x in this case is 0, and we're adding to that 1.5. Applying our BODMAS, we can clearly see that's a value of 1.5. So when x is equal to 0, we get a value of 1.5 here. When x is equal to positive 2, then y is simply equal to 2.5 multiplied by 2, and we're adding again 1.5. Again, be careful applying your BODMAS. We've got to deal with the multiplication first. So 2.5 multiplied by 2 is 5, add 1.5, which is equal to 6.5. So when x is equal to 2, y is equal to 6.5. I'll evaluate one more coordinate with you. This time when x is equal to negative 1, let's find the value of y. So y is equal to 2.5 multiplied by negative 1 plus my 1.5. So be careful with your BODMAS and your directed numbers here. We've got 2.5 multiplied by negative 1, so that's negative 2.5, and then we're adding 1.5 to that. So that becomes negative 1. So in our table, when x is equal to negative 1, y is also negative 1 in this case. I will leave you to work out the final coordinate. When x is equal to 1, I'll let you determine the value of y. And you can also now check the first coordinate given. When x is equal to negative 2, y is equal to negative 3.5. So what we've done here is determine 5 coordinates for the function y is equal to 2.5x plus 1.5. That's an equation to a linear line. From here we can now plot these points on a graph and draw the line. We will show the plotted graphs a bit later in the presentation. Exercise 1 is continued here. We're given 3 more functions. Function b, y is equal to 2x minus 3. Function c, y is equal to negative a half x minus 1. The equation could be written as y is equal to negative x divided by 2 minus 1. That helps you with your calculations. And finally, we're given in your function d here, y is equal to x. For each of the equations, make sure you clearly state the values m and c, noting that each equation has the form y equals mx plus c. I suggest you stop the presentation and complete the tables, but I will show the answers on the following slide. So here's exercise 1. The solutions to each of the lines A, B, C and D are shown here. We covered equation A on the previous slides, but equation B is shown here. So hopefully you have m is equal to 2 in this case, and the c is equal to negative 3. The y value is shown here in the table. For part C, we're given the equation y is equal to negative half x minus 1. So in this case, the m is negative a half, or negative 0.5 in decimals, and the c is negative 1. Make sure you've written it as negative 1. Again, the y values are shown in the table. And finally, for the equation D, the function is y is equal to x. I put this one last, although it's the simplest of the equations, because students sometimes have difficulty in extracting the m and the c here. But basically you can think of a 1 being in front of the x, and if you think of a plus 0 here, then you have the form of y equals to mx plus c, where m in this case is 1, and the c in this case is 0. And again, the y values are shown here. The y is equal to x function plots a 45-degree line passing through the origin. So what I want you to do now is start the presentation and plot functions a, b, c and d on the same graph, and then we can look at the variation in the lines. Just note, when plotting all of these functions on the same graph, we obviously need to know the maximum height in the y direction and the maximum width in the x direction. So looking at my graphs, I can see so the width of the graph we need to plot on the horizontal axis will be between negative 2 and positive 2, because that's given in the question. But looking for the range on the vertical axis, we can see that the maximum y value in our table is positive 6.5, and the minimum y value in our tables is negative 7. So I would suggest to plot the graph up to 7 and down to negative 7, using increments of 1. When you're plotting the functions, try and use the extent of the graph paper for your x and y ranges, because that makes the graph easier to plot and also easier to use. If you're having trouble working out the actual y value shown in the tables, on the following slides I'll show you the actual calculations for your reference. Exercise 1 continued. I'm just going to show you very briefly the actual calculations that were undertaken for each of the functions. So for part A of the question, our function y is equal to 2.5x plus 1.5. Here are the calculations for the various values of y, and given the various values of x on the left hand side here. I'll let you review that at your own pace. Exercise 1, part B. Here's our function y is equal to 2x minus 3, and again the calculations for you to review at your own pace. Exercise 1, part C, the y is equal to negative a half x minus 1. The calculations for you to review for calculating the y values. And finally, exercise 1, part D, the function y is equal to x. Much more straightforward to evaluate. Exercise 1 continued. Here is the graph that shows the 4 functions plotted, the a, b, c and d. I've tried to colour code them for convenience. Just considering the gradients of m's, I've got 2.5 for line A. There's line A here, so the gradient here is 2.5. If we compare that to the gradient of line B, which is the y is equal to 2x minus 1, when the gradient is 2, that's line B here, you can see that the A line is slightly steeper than the B line, which we would expect because the gradient is slightly bigger for the A line. For line C, the y is equal to negative half x minus 1. Gradient here is obviously a negative value, so you can see the direction of the line has changed here. And finally, line D, we know that's y is equal to x. That's the y is equal to 1x, if you like. So that's actually a 45-degree line here going through the origin in this case. We now consider the intercepts, which don't forget is with the y-axis. For line A, the intercept should be positive 1.5, which we can see here. The line A crosses the vertical axis at 1.5. For line B, the intercept should be negative 3, and we can see the line crosses the vertical axis at negative 3. For line C, we can see the intercept is negative 1. For line C, intercept here is negative 1. And obviously for line D, the intercept will be at 0. There is no constant there, and that's what we see the graph passing through 0. So that's plotting lines given the original functions. Exercise 2, we're asked to calculate 3 points on each of the following lines and then plot the function. It's suggested that we use the 3 points at x is equal to negative 1, x is equal to 0, and x is equal to positive 2. We're given 5 functions here. A is y is equal to 2x, B, y is equal to 5x, C, y is equal to a fifth of x, which could be written as x upon 5 for your reference. Part D, y is equal to negative x, and then part E, y is equal to negative 3. So we need to work out the y values for each of the x values given, and encourage you to stop the presentation and attempt that exercise. The coordinates are shown on the following slide. Exercise 2, here is the solution. For each of the x values given, that was negative 1, 0 and positive 2, we're asked to work out the y coordinates for the various graphs, and they're calculated for us in the table. I suggest you start the presentation and just check your values against the coordinates shown in the table. Just note for reference that when the equation was y is equal to negative 3, then the y values are always negative 3. That's a horizontal line passing through negative 3 on the vertical axis. In other words, there is no x term in that equation. Exercise 2 continued, and here's the plot of the various graphs. What you'll notice is the steeper the value of m, when m is equal to 5, it's a very steep graph. It's a 5 in 1 graph. When x is equal to x upon 5, that's a very shallow graph. A gradient is 0.2 actually, or a fifth. So that will give you a line somewhere down here. When x is equal to the negative x, that's a 45-degree line passing through the origin, but that's in this sense now, because it's a negative gradient. And when y is equal to negative 3, that's a horizontal line passing through negative 3 on the y-axis. So what this little exercise is trying to show us is that the bigger the m, the steeper the gradient, and a positive gradient is like walking up a hill from left to right. When the m is negative, that's like walking downhill from left to right. And when there is no x term in the equation, we have a horizontal line. In the next part of the presentation, we're going to consider evaluating the gradient or the slope of a line, finding its intercept, and writing down the equation to the line. So as mentioned previously, if you want to calculate the gradient of a line, you need to take 2 points that lie on the line. I've labelled them 1 and 2 here for convenience. And then we work out the vertical distance between the 2 points, label that delta y. The horizontal distance between the 2 points, label that delta x. And then dividing the delta y by the delta x, we can calculate the gradient m. An alternative, and I think preferable way of working out the gradient of a line m is to use this equation shown here. y2 minus y1, so that's the y coordinate for point 2, take away the y coordinate for point 1, divided by x2 minus x1, where that's the x coordinate for point 2, subtract the x coordinate for point 1. I would encourage you to try and remember this equation, to use this equation to work out the gradient of a straight line, as this method always works out the sense of the line, whether it's positive or negative. When students use this approach, the delta y by delta x, it will work out the gradient, but with this method you have to think through whether the gradient is positive or negative. With this method, it works it out for you. So I'd encourage you to use this equation. So if we use this equation and put the values in, from the table above, the y coordinate for point 2 is 4, so that becomes 4. And we're subtracting from that the y1 coordinate, point 1, the y1 is 3. And that's all divided by the x2 coordinate is point 2, the x coordinate is 6. So that's 6. And we're subtracting from that the x coordinate for point 1, which is 2. Just evaluate the numerator and denominator. 4 minus 3 is 1, and that's divided by 6 minus 2 is 4. So the gradient is 1/4 or 0.25 in decimal. Just note for your reference, it doesn't matter in which order you label the points 1 and 2. And again, this is just a recap here of positive and negative gradients for your information. As I mentioned previously, a positive gradient, that's a positive value of m, would have a sense like this. In other words, walking up a hill, moving from left to right. A negative gradient, so a negative value of m, would be like walking down a hill from left to right. A zero gradient, something like y is equal to 3, we looked at on the previous slide, that's where m is equal to 0. That would plot a horizontal line passing through, in this case it would be 3. The vertical line shown here is sometimes termed an infinite gradient, where the m is equal to infinity. Designated x is equal to a constant, in this case a. In example 1, we're given 2 points, read this as x, y, that's 4, 16, so that's x is 4 and y is 16, and we're also given the coordinate 2, 6, so x is 2 and y is equal to 6, and we're asked to find the equation of the line. So I'm going to show you 2 solutions here using the points. The first solution is a graphical method, and the second solution is an analytical method. So solution 1, we've plotted these points and extended the line to produce the graph shown over here on the right hand side here. So here are the 2 points. I've labelled them 1 and 2 for convenience. This is point 1 when x is equal to 2, y is equal to 6. And this is point 2 when x is equal to 4, y is equal to 16. What we're going to do is work out the gradient of the line. So what we're going to do here is work out the vertical distance between the 2 lines. We're calling that delta y here. So delta y would be the 16 on the vertical axis, subtract the 6 on the horizontal axis to give us the value of 10. So delta y in this case is 10. And the delta x is 2, because on the horizontal axis for point 2, the x value is 4, and for point 1, the x value is 2. So 4 take away 2 is 2. So delta x in this case is 2. Evaluating, we find the gradient is 5. Just for reference, if you wanted to use the equation on the previous slide, that m is equal to the y1 minus the y2 divided by the x1 minus the x2, that evaluates to 5 for the gradient. To find the intercept for this line, we simply look where the line crosses the vertical axis, and obviously crosses here at -4. So the intercept in this case is -4. So now writing the equation of the line down in the form y equals mx plus c, the equation would be y is equal to 5x minus 4. So now we've evaluated the equation of the line using our graphical approach. Here is solution 2, an alternative approach to calculating the equation of the line. What we're going to do here is generate 2 simultaneous equations from the information given, the 2 points given. We know the equation of the line is y is equal to mx plus c. So we're going to be able to solve for the gradient, the m, and the intercept, the c, directly. We have looked at solving simultaneous equations in a previous presentation, which I would encourage you to review if you want to recap on simultaneous equations. I will very briefly take you through the process here, but we are concentrating primarily on graphical methods in this presentation. So given the first point, 4, 16, we know the x is equal to 4 and the y is equal to 16. All I do is put that into the equation of y equals mx plus c. So on the left hand side there's my y, which is 16, and then my x value in this case would be 4, so 4m plus my c, which I do not know. I've called that equation 1. Consider the next point, which is 2, 6. So in this case, the x is 2 and the y is 6. So again, writing those values into the equation y equals mx plus c, that becomes the 6 is the y is equal to 2m plus, again, the c we do not know. I've called that equation 2. I'm going to use what's called the elimination process, that we looked at in the previous presentation, to solve this. These are actually very simple equations to solve using this process because you have the same coefficients associated with the c in all these cases. In other words, the coefficient associated with the c values are both 1. I can simply subtract the equations to eliminate the constant c and solve for m. So in this case, 16 minus the 6 gives us 10. 4m minus 2m is 2m, and obviously c minus c is 0. Dividing both sides by 2, then m is equal to 5, as we found from the previous solution. Because we're using simultaneous equations here, we can simply back substitute the value of m into either equation 1 or 2. I've chosen to substitute the value of m into equation 2 here, so m is 5 into equation 2, and again we can solve that directly for the constant c, which is -4. Finally, we can write down the equation of the line, which again would be y is equal to 5x minus 4. Solution 2 is an alternative method for finding the equation of the line without actually referring to a graph. This is termed an analytical method. And again, for your reference, we looked at this method of solution in a previous presentation. Exercise 4, we're asked to plot the following points and then determine the law of the line, the equation of the line, which should be of the form y is equal to mx plus c. So questions 1 through to 9 here, we're given 2 coordinates in each of the questions. So in the first question, we're given the point 1, 4 and 0, 0. We're asked to plot that, and from that work out the gradient, the intercept, and then state the equation or the law of the line. I've just repeated the gradient equation m here for convenience if you want to use that to work out the gradients given the 2 points. I would encourage you to start the presentation and plot these points and so work out the equation or the law of the line. Just notice in question 9 it does state to find the law of the line using simultaneous equations. So if you want to use the method shown on the previous slide in solution 2, I would encourage you to attempt it for part 9. I have included some solutions to exercise 4 on the following slides. Here's a solution to exercise 4 part 1. I'm showing a sketch on the left hand side using the 2 coordinates given to us. In the center column I'm working out the gradient or the slope using our equation, and on the right hand side I'm stating the constant c. In exercise 4 part 1 we'll find the gradient m is equal to 4, the intercept is 0, so the equation to the line is y is equal to 4x plus 0, or simply y is equal to 4x. Exercise 4, part 3. I'll let you look at this solution at your own pace. You should find the equation of the line is y is equal to 2x. Exercise 4, part 5. The equation of the line is y is equal to 0.6x plus 2 in this case. The intercept is 2 here and the gradient m is 0.6. And exercise 4, part 8 here. Graph is plotted on the left hand side. The m is calculated here is -1.5 and the intercept is -2. So the equation of the line is y is equal to -1.5x minus 2. In the earlier part of this presentation, we were given the equation to a line in the form of y equals mx plus c, and a range of x values, and from that we could work out the associated y values and plot the line on a graph. What we're going to look at here is plotting a line, but this time from given data. So in this table we're given a range of x values and associated y values, and we're asked to plot the coordinates, and from that draw the best fit straight line we can through the points, and so determine the gradient of the line and its intercept. And ultimately we'll write the equation down in the form of y equals mx plus c. So on the left hand side here I've got a 10-step process which we're now going to undertake to determine the equation of the line and given the data in the table above. So step 1 of our process, we're initially going to review the coordinates given in the table on the right hand side and decide on the range of x values and y values that we're going to plot. In step 2 we're going to choose the suitable increments for each of the axes. So for example, increments of 1, 2, 5, 10, 20, 100, etc. acceptable. But we avoid increments such as 3, 7 and 9 because they're more difficult to plot and also interpret. Note the increments can be different on the x and y axis. So considering the x values in our table, they range from 8 through to 50. So I would suggest on the horizontal axis we will have a range of 0 to 50 and use increments of 10. And considering our y values in the table, they range from 180 through to 600. So I suggest on the vertical axis we have a scale of 0 to 600 and use increments of 100. So here's a sketch of the graph I propose to use here. On the x-axis here we have a scale from 0 to 50 in increments of 10. And on the vertical axis here, the y-axis, we have a scale from 0 to 500 in increments of 100. So we have different increments on the axes, but that is fine. That suits the information that we're given. Referring back to our procedure, step 3 states that we should make the graph as large as possible because that makes it easier to plot the coordinates and also to interpret the final graph. And step 4 suggests we should label the axis stating units and add appropriate title to the graph. So because in the table above we're not given any labels or units, I've just simply called my horizontal axis x and my vertical axis y. But in a contextualized question we could have on the vertical axis velocity and the horizontal axis we could have time. So our velocity axis would be labelled v in meters per second and our horizontal axis will be labelled in t in seconds. We would then have the chart title saying velocity plotted against time. But in this case we've got no further information about the values given, so I'm just going to keep my axes as labelled x and y. Step 5, we need to plot all the coordinates given in the table on our graph as accurately as possible. So if you're plotting the graph by hand, I would encourage you to use graph paper because that will allow you to be more accurate in the way you plot your coordinates. But in my table here I've taken the first coordinate of 8 on the x-axis and 180 on the y-axis, and I've tried to plot that to the scale I'm using in my little sketch here. Taking the next coordinate of 19 on the x-axis and 220 on the y-axis, and again I've tried to plot that to scale on my diagram. I've plotted all 5 coordinates given to me in the table above. Step 6 in our procedure, we're now going to draw the best fit line through the points, being aware that not all the points, if any of the points, might lie on the line. And also we're not going to force the line to pass through the origin 0, 0 down here. Step 7, if required, we need to extrapolate the best fit line so that it crosses the y-axis, and that allows us to find the intercept constant, which we will label as c. Now step 8, we're asked to choose any 2 points that lie on the best fit line that are convenient for us to find the associated x and y values from the axes, and we're going to label them as points 1 and 2. In the diagram you can see I've chosen 2 points here on my best fit line and I've labelled them as 1 and 2. That's an arbitrary label. So step 9 of our procedure, we're now going to calculate the gradient, that's the m value of our best fit line using the formula shown here. So gradient m is equal to the y2 value minus the y1 value, all divided by the x2 value minus the x1 value. So on the graph, for my 2 points I'm considering that lie on my best fit line, I've determined that the x value for point 1 is 20, and the y value for point 1 is 300, and the x value for point 2 is 40, and the y value for point 2 is 500. And we'll simply put those values into the equation for m, so 500 minus 300 on the vertical axis, and 40 minus 20 on the horizontal axis. That gives me a value of m of 10. And that would have units depending on the units of the y and x axes. By inspection of the best fit line with the vertical axis, it would appear that the intercept occurs at 150. So our c value is 150. So finally, step 10. Now we know the gradient, the m, the intercept, the c. We can write down the linear equation to our best fit line in the form of y is equal to mx plus c. So here's the equation we've derived from the data. Y is equal to 10x plus 150. Just note for reference, now we have the equation to the line. We can be given any value of x and insert it into the right hand side of the equation and calculate the associated value of y. So once the equation to the line has been found, we can then use the equation to find any value of y and given the value of x. Now some of the later questions will ask you to use the equation you derived from the data. Question related to the context of experimental work. So a useful application of the straight line law is to determine the law that connects two quantities when experimental values have been obtained. So in exercise 5 here, we've got a test on a metal filament lamp, and the results are shown in the table. Resistance R in ohms against the voltage V volts. The results are expected to agree with an equation of the form R is equal to mv plus c, where m and c are constants. We know that m is equal to the gradient and c is equal to the intercept. So in this particular question, they've changed the notation on. Instead of having y equals mx plus c, we have r is equal to mv plus c. So it's the equation of the line that defines the x and the y axis. So in this case, the r would be the y-axis and the v would be the horizontal axis. So what we need to do here is plot the 5 points given on a Cartesian graph, an xy graph. Draw the best fit line we can through the points, bearing in mind that none of the points may actually lie on the best fit line. And then we'll pick 2 points on our line that we've drawn, and from there we'll work out the gradient and the intercept as we've shown in the previous slides. I would encourage you to start the presentation and plot the points given on the diagram, making sure that the R is on the vertical axis and the V is on the horizontal axis. And from there we can start to evaluate the equation of the line. Because we're using a graphical method here, we will need to start our graph at the origin 0, 0, even though the first point plotted starts at 62 on the horizontal axis, because we will need to extrapolate our line back to the vertical y-axis to find the intercept. For your reference, a graph of the points plotted is on the next slide. Exercise 5 solution. Here's a graph of the resistance R in ohms on the vertical axis plotted against the voltage V in volts on the horizontal axis. The horizontal axis shown starts at 60 on this slide, but hopefully you have started from the value of V is equal to 0 on your graph. So hopefully what you've done is extrapolated your line back to where it hits the vertical axis, and from that you will just read off the value of R. I'm going to work out the gradient using the 2 points of P and Q. So using the equation on the previous slide, m is equal to y2 minus y1 over x2 minus x1. I'm going to call this point 1, point 2. So putting the values to the equation, m is equal to, so evaluating the gradient, m is equal to 1.275, and units would be ohms per volt in this case, ohms on the vertical axis and volts on the horizontal axis. And if you've extrapolated the line back to hit the vertical axis, you should find the C value in this case is around about 22 ohms. So for completeness, stating the equation to the line in this case, R would equal to 1.275V plus around about 22 for the constant. And that of course would be ohms. On the following slide, we'll show the analytical solution for reference. Exercise 5 repeated here, but this is the analytical solution. So in this solution, we're going to take 2 points labelled P and Q on the sketch and solve for the values of gradient M and intercept constant C. The process we use for generating the 2 equations, one labelled here, 2 labelled here, is very similar to that we used previously. I would encourage you to start the presentation now and follow through the solution at your own pace, noting that the value of gradient M in this case will be 1.275 ohms per volt, and the intercept constant C found by back substituting the value of M into equation 1 is 21.75 ohms. Just for reference, some students find it difficult to actually state the unit of the gradient. The unit is simply found by dividing the vertical axis units by the horizontal axis unit. So in this case, the unit of M would be ohms, that's the resistance on the vertical axis, divided by the voltage, that's the volts on the horizontal axis. The units of C, of course, relate to the units of the y-axis, so it's ohms in this case. So now we've determined the values of M and C, we can write them into the equation. And units of R, of course, are ohms. Exercise 6, read the question carefully and plot the velocity against time, as stated in the question, from which you have to find the relationship between the variables, and we're told the relationship is of the form v velocity is equal to mt for time plus the constant c. I suggest you plot the 7 points in the table appropriately on a graph and use a graphical method to solve for the equation of the line. The answer is given in the bracket on the right hand side. Just be careful the way the answer is actually specified in the question. I will show you the full solution on the following slide. Here's the exercise 6 solution. Here's the graph plotted of the points. They seem to lie nicely on the line. You can clearly see the intercept in this particular case is 3. So the gradient of the line is obviously negative because of its direction. And if you work out the gradient, you should find the gradient is -7. So notice the way the equation is written. It's actually written as v is equal to 3 minus 7t. So that's actually written in the form of y is equal to c plus mx in this case. They've written it that way purely because a positive number normally comes in front of a negative number within mathematics. But there's nothing wrong with writing the equation in the form v is equal to -7t plus 3. I'd encourage you to check that solution for yourself. Just a few general points relating to plotting of a graph. Graphs are extensively used in engineering. They display information nice and clearly and concisely to engineers, so we need to make sure they are formally structured and formally presented. All graphs should have a title that should explain the information being displayed. Layout. Ensure the full use of any graph paper is used. The larger the graph, the increased accuracy. Scales. We choose appropriate scales that are easy to work from. Preferable to let 1 unit of a graph equal to something like 1, 2, 5 or 10 increments, because that aids clarity and interpolation activities. Try and avoid scales where 1 unit represents 3, 7 or 9, because they're much more difficult to use in practice. Don't forget the scales on the x and y axis can be different. You could have increments of 10 on the x axis and increments of 1 on the y axis. Choose suitable scales to fit the data you're considering. Consider the origin. Where possible, we start one or both of our scales from 0, but we don't do that if that would result in the points being plotted in one small corner of the graph paper. Label axes. All axes should be very clearly labelled and appropriate units stated as required. Ensure there's enough figures along each of the axes to help with reading of the graph and also aid in interpolation if that's required. Try not to overcrowd the figures along the axes. And finally, the points. Suggested to mark each point on the graph with a cross sign where the intersection of the cross is exactly on the location required. Alternatively, we could mark each point on the graph using a very fine dot to mark the exact spot with a circle around it to make it easy to find. That's just some tips and wrinkles when you're plotting graphs and presenting them to other engineers or in reports. Here are some tutorial questions I will leave you with. Question 1 here through to question 3. I would encourage you to stop the presentation and attempt these questions. The answers are shown on the right hand side in the square brackets. Question 4 relates to a practical engineering context related to keyways on various shafts. The approach is the same now as in all the previous questions. You're given some coordinates to plot. This time you have D and W as your variables. W will be on the vertical axis and D will be on the horizontal. And your A and B here, read that as M and C in our previous work. I'd encourage you to start the presentation, attempt this question, plot the points given in the table below, draw your best fit line you can through the points, then take 2 points on your best fit line, and then from that work out the gradient and the intercept. Answers are shown in the brackets below. And question 5 and question 6 I will leave you with. Question 5, you have to find the gradient and the intercept, and then write the equation of the line. And question 6, you have to do the same, you have to find the equation of the line. The last part of the question is simply actually using the law of the line you found by putting the appropriate values into the equation. Here's the bibliography used to help generate this presentation. Some very good engineering textbooks here. I hope this has been of use to you and thank you for viewing.